Hello and welcome to this clip on the nucleophilic addition reaction of hydrogen cyanide to carbonyls, essentially the synthesis of nitriles. So we're going to cover the formation of the cyanide ion in the first place, which is C triple bond N. I'm just going to pop the triple bond in there, like so. The mechanism of nucleophilic addition of this particular ion onto aldehydes and ketones to form hydroxynitriles, and the significance of this reaction in organic synthesis, because what we're doing is we're adding further carbon atoms directly onto an existing alkyl chain by the creation of a new carbon-carbon bond. So it's a very important and significant reaction in organic synthesis to be aware of. So the first thing to do is to actually look at the dot-cross diagram of HCN, which is straightforward enough, as you can see on the left. As you expect, you have a triple bond, so you have an alternation of dots and crosses between the carbon and the nitrogen, and a straightforward covalent bond between the carbon and the hydrogen. So this makes sure that each atom has its full complement of an outer shell of valence electrons, 2 for the hydrogen and 8 each for the carbon and the nitrogen. On the nitrogen we have a lone pair, as you can see, but if you were to break that up, if we were to break up HCN into the cyanide ion and H+, looking at the cyanide ion itself just for a moment, the extra gained electron is actually gained by the carbon. So that means the carbon becomes negatively charged. If it becomes negatively charged, then it's the carbon that's going to behave as the nucleophile whilst it's attached to the nitrogen. Even though the nitrogen has a lone pair, the carbon's lone pair makes the carbon itself negatively charged. So it's the part of the ion which will be attracted to the delta positive carbon in C double bond O. So what this creates is a compound called a nitrile. So the important thing about the nitrile is that it actually creates a new carbon-carbon single bond, which is being highlighted at the moment. So the mechanism that we've got here is called nucleophilic addition, because the C triple bond N behaves as a nucleophile. And like we've mentioned already in the introduction, it's used extensively in organic synthesis to extend alkyl chains by 1 carbon atom each time. Afterwards, the nitrogen can be removed and swapped for something else, but essentially what you've got is an additional carbon in the chain. So you can see quite clearly at the start you've got 1 carbon, at the end you've got 2 carbons. So this is the significance of this particular reaction. So a slight problem with making the cyanide ion, C triple bond N, is that its creation from hydrocyanic acid, or HCN, is in equilibrium. It's a weak acid, so it doesn't readily dissociate. So we have to try and encourage the equilibrium to shift to the right so the desired nucleophile is actually formed. I've highlighted it here in black. So if we react the HCN with an alkali, what that does is it forces the equilibrium to go to the right, because it's removing H+ ions. So if it's removing H+ ions, forcing the equilibrium to go to the right, it's also forcing it to make more cyanide, which is what we want. However, the downside of this is that hydrogen cyanide, or HCN, is a very toxic gas. The cyanide ion interferes with enzymes responsible for respiration, so it effectively shuts cells down. It doesn't take much at all to actually kill people. So what we do sometimes instead is use sodium cyanide in acidic solution. The cyanide ion is still present, it's obviously still toxic, but it's slightly easier to handle in a practical way than having something floating around as a gas that's lethal. So although this is a perfectly good image that I've got hold of on the internet, I'm going to do a slightly improved version that shows the C triple bond N a little bit more clearly. So the first two things that happen is the lone pair on the carbon atom in the cyanide ion is attracted to a partially positive carbon atom in C double bond O. The pi bond in C double bond O then breaks and the electrons move on to the oxygen. This makes the oxygen negatively charged. So the lone pair on the oxygen atom of C single bond O moves towards partially positive hydrogen atom in water. So what happens is a bond is created between the oxygen and one of the hydrogens that allows the oxygen-hydrogen bond in water to break, releasing a hydroxide ion. So your final organic product is called a hydroxynitrile. It contains a nitrile functional group, C triple bond N, and also a hydroxyl functional group, OH. So it's worth pointing out in the second stage, if sodium cyanide had been the source of the nucleophile, it would be H plus that would be reacting instead, not water. The reason for this is, like we said in the previous slide, that if sodium cyanide is used, it's dissolved in an acidic solution to provide that proton with which the oxygen can actually react with. And just before we go on to the next slide, I just had to slightly adjust a couple of my labels there and annotations because they weren't fully clear on the screen. So sorry about that. Hopefully now you can actually read it and it makes a little bit more sense. So let's have a look at an example of a typical exam style question. The first part's easy enough, saying giving the mechanism for the reaction between ethanol and hydrogen cyanide. But what's interesting is it's in the presence of a little alkali. So it's obviously saying that it's HCN dissolved in some sodium hydroxide or something like that, sodium hydroxide solution. First thing I do is I draw my ethanol with the dipoles on the carbonyl group on the C double bond O. And draw my nucleophile in the vicinity, so I can draw my curly arrow nice and easily from between the two electrons of the lone pair on the carbon onto the slightly positive carbon of the carbonyl group. So the next thing I do is draw the intermediate. So the newly negatively charged oxygen possesses an extra lone pair now, which can be pressed into action, and that lone pair is attracted to a proton. The proton would be from the HCN. I'll do how the HCN dissociates in a second, because it's obviously a 6-mark question, because there's quite a bit of detail involved, I think. So the next thing to happen is you have your hydroxynitrile formed, like so. So that will probably be about 4 marks or 5 marks so far. The 6th mark is for saying how the C triple bond N is generated. Because remember, at the beginning of the question, we highlighted, didn't we, that it was in the presence of a little alkali. So that has to be paid respect to in the question's answer somehow. So either of those two examples would do. Obviously, in my particular mechanism, I've chosen to use this time the H+, because earlier on in the clip, I showed you how you might want to use it using water. So I've opted to this time use H+. You end up with the same thing, it's just you don't get an OH minus produced at the end like you would if you involved water. So then the next part of the question asks you, why can't it be carried out with pure hydrogen cyanide? So for this particular question, they probably want something a little bit more sophisticated for just the fact it's toxic. The practical reason is that it's a molecule, hydrogen cyanide. It hasn't dissociated into H plus and C triple bond N yet. So the carbon atom has no lone pair on it. If you remember earlier in the clip, we showed the dot cross diagram for HCN and there were no lone pairs on the carbon. So it can't act as a nucleophile until a lone pair on the carbon is actually formed. That would have to happen once it's actually dissociated. So let's look at the next part of the question by moving the page down a little bit. It says the reaction occurs best when the conditions are slightly acidic, but if the pH is either too high or too low, the reaction is slowed down, and it asks you to suggest reasons why this might be the case. So at low pH, we have a lot of H plus present. At high pH, we have a lot of OH minus present. So it can also be considered in terms of high or low H plus concentration. Now I know that H plus is a key player in the equilibrium, in the sense that it's involved very fundamentally in the equilibrium like that. So at low pH, the equilibrium is distributed to the left-hand side. So at low pH, the equilibrium will shift to the left-hand side to favour the formation of HCN, because the concentration of H plus is high, so according to the Chatelier's principle, the equilibrium will shift so as to counteract this by using up H plus and also Cn minus. This will slow the reaction down. So at high pH values, the concentration of H plus will be low, and therefore the reaction will proceed very slowly at the second stage. So I'm talking here about where the intermediate interacts with H plus to form the OH hydroxy group. So that will actually slow things down for that reason. So hopefully this has been a fairly useful clip. Let's have a quick look at the mark scheme on this to make sure that we're in the right place. So by and large, the answers that we've looked at are the ones that are in front of us. I've slightly altered the way I've drawn the mechanisms. For example, in this part of the mechanism, it's slightly preferable for our specification to have the curly arrow starting from between the two electrons in the lone pair. But apart from that, it's fine. All of the logic we've talked about, all the ideas we talked about are contained in the mark scheme. I just had to slightly adjust and put a little bit of a caveat in there to make sure that the answers that we're giving are specific to our particular specification. This is a general worksheet, a general exam style question. So hopefully it's been of some use to take you through this reaction. If you have any further queries, obviously bring them to class, have a chat to your teacher, come and see one of us in a subject extension at college. But in the meantime, thanks for your time, thanks for listening, and see you soon. Bye.